So here on page 7, we have a lot of notes about polarity, and I'm just going to go over them here in this video in case you were absent or in case you didn't quite understand them. And then I will go over some practice problems on page 4 with you to help you understand it a little bit better. And then remember that you are supposed to go and circle the rest of the polar nonpolars on pages 5 and 6 as well. So polarity starts at bond polarity. And we've talked about the polarity of bonds, how we can have polar covalent bonds and nonpolar covalent bonds since back at the beginning of Unit 4. And this is that same idea. It comes back to the electronegativity difference between the elements. And I have this little diagram there in your packet to help you see that difference. If I have a nonpolar molecule with no electronegativity difference between our atoms, this bond is nonpolar because each of my atoms are pulling on the electrons the same amount. They're still shared electrons, and because they have equal strength, equal electronegativities, this electron cloud is very evenly shaped around each of them. It's just a bigger cloud encompassing both now that they're sharing their electrons. Polar covalent bonds, on the other hand, have an electronegativity difference between the atoms that are in that bond, which means that one of them, in this case this one on the right, has a larger electronegativity. It's stronger, it's going to pull harder on the electrons, which means they're going to spend more time, and it's going to have a larger portion of the electron cloud than the one with the smaller electronegativity. So when we have any kind of difference that makes our bond polar. Technically, we also have those ionic bonds that are kind of super polar. They have an even larger electronegativity difference than our polar covalent bonds, so much so that that atom on the right doesn't just hog the electrons, it steals them. Remember how we were drawing arrows showing the transfer of electrons back when we were doing the ionic Lewis dots. So they start one place, they end up another place. There's no sharing going on. There's such a big difference in the strength that weaker atom has no chance of holding on to the atoms or the electrons in that bond. Now, bond polarity is the simplest case of polarity, but what we really care about is whether the molecule that we're drawing is polar or not, the overall polarity for our molecule. And this does come back to those polarity of the bonds, but we can have a nonpolar molecule that has polar bonds. But the simplest case would be if I have all nonpolar bonds. If our molecule is only nonpolar bonds, all nonpolar bonds, no polar bonds in it, then that means that the whole molecule is going to be nonpolar. There's nothing polar in it. It has no chance of being polar. Most of the time, we're going to have polar bonds, though, and so what we really need to figure out is whether or not they're going to cancel each other out in order to have an even distribution or uneven in the case of our polar. Now, this is a little bit high level. This is what you would have to do if you were in college in order to analyze much more complicated molecules to see if they have polarity. So we can actually look at the polarity of each of the bonds and draw arrows towards the more electronegative element, showing the direction that the electrons are being pulled more. And if our polar bonds, in the case of CO2, are pointing the opposite directions, they're canceling each other out, which is why CO2 can have polar bonds, but it's a nonpolar molecule. H2O here has these two polar bonds, but because they don't directly cancel each other out, they're not equal and opposite, then we do end up having more electrons spending more time around the oxygen and less around those hydrogens. Now, this is one of those times when knowing our electron and molecular geometries would help, because if I had been looking at H2O the way that I normally draw it out at nice right angles, this would look linear, and this would look like our arrows would cancel each other out. But understanding that this is actually a bent molecular geometry, that these aren't exactly equal and opposite, so they're not going to cancel out, would be important there in order to be able to tell that this is a polar molecule. So that can be kind of complicated, and it's a little bit overcomplicated to draw all those arrows for the simple molecules that we have. You can really come down to answering two simple questions to figure out if our molecule is polar or nonpolar. And before I even get into what these questions are, look at the format of the flowchart. In order to be nonpolar and actually get down to the point where my answer is that I am nonpolar, I have to start by asking my first question and get a no, and then answer my second question and also get a no. So we have to say no to both of these questions to be nonpolar. But notice that as soon as I say yes to either of these questions, then my molecule is instantly going to be polar. So all that we're going to be looking for, the questions we have to ask ourselves when we're looking at our molecule is, are there lone pairs on the central atom? If I do, you know that's going to be bending my line into a bent shape or my triangle into a pyramid shape. And that's going to cause an uneven distribution of electrons, just all on its own. Instantly, yes, we're polar if there's any dots, any lone pairs on that center atom. The other question that we need to ask is if any of those outer atoms are different from each other. So we're going to see examples of this down below, but remember that most of our structures, we start by binding things, connecting things to the central atom, and all it would take to be polar is for one of those groups to be different. So in this case, with my 3 H's around the outside, no lone pairs on my central atom, this would be nonpolar. But if just one of these was a Cl or an F or anything other than an H, having that different atom around the outside instantly makes my molecule polar. Now, we've talked about diatomic molecules and how sometimes they're a little bit special cases, and this is no different. And honestly, these are simpler cases, simpler molecules, but when you look at them, sometimes it just doesn't seem to fit because everything here is talking about looking at a central atom or outer atoms, and diatomic molecules don't have them. So if it is just a diatomic molecule, like H2 or Cl2, or here we have HF listed as an example, all of these just have 2 atoms. If those 2 atoms are the same, then it's nonpolar. If they're different, then it's polar. That's what it comes down to. That's all that it is. And this is really just comes back to the bond polarity. If all I've got is 2 atoms bonded together in that diatomic molecule, then the bond polarity will be the molecule polarity. There's no chance of other bonds canceling out the polarity of that bond. So just look and see if the elements are the same, and that will get you that answer. So we have a few examples down here at the bottom of the page that we'll do before we move to page 4. And I'm going to draw the structures out or have them pop up really to remind you what they are. It might be helpful to draw them out so you can see them there, and because that's what we have to do to see lone pairs or see if our outer atoms are different. But you do not have to. As long as you get the polar, nonpolar answers by each of these, then I'm fine. You'll get full credit in your packet, but it might be helpful to draw them so you have that frame of reference. So this SiO2, if I start at the top, there are no lone pairs on my central atom. There's some on my outer atoms, but those don't matter. Then, are my outer atoms different? No. So I've said no, no. That brings me down to nonpolar as my answer here. With Br2s, I instantly see that I do have lone pairs on my central atom. So instantly, before I even have to look at those outer atoms, it doesn't matter anymore. As soon as I see a lone pair on my center atom, then it's polar. In CCl4, I have got lots of lone pairs again, but none of them are on my central atom, so that's first a no. And then, are my outer atoms different? No. So this is non-polar. CH2Cl2 is very similar to CCl4. There's still no lone pairs on my center atom, but this time my outer atoms are different, and you could probably tell that they were going to be different before you even drew the structure because of that formula and the way it's drawn. So that is polar, and you might not have to draw out that structure to see it, but drawing the structure can give you more confidence in that answer. pH3, I have lone pairs on my central atom. That makes me polar. BH3 looks pretty similar, but remember that boron is happy with just 6, so it doesn't need any double bonds, no lone pairs on that B. So BH3 just looks like this. No lone pairs on my central atom, no different atoms around the outside, so this is non-polar. That's really all there is to it. You gotta draw the structure, and then you're just asking yourself these same 2 questions over and over again. So let's look at some more molecules on page 4. I have these all drawn out. Let me know in class if you have questions about these structures, but here we see no lone pairs on carbon. The outer atoms are not different, so this is non-polar. In H2O, I do have lone pairs on my central atom, so that's polar. No lone pairs on my central atom, no different atoms around the outside. No means non-polar. CCl4 we've already seen. It does not have any lone pairs on our central atom, and it does not have different atoms around the outside, so it is once again non-polar. NH3, I have a lone pair on my central atom, so that makes it polar. And then HF, wait, I don't have a central atom here. Oh, that's right. That means this is diatomic. I just have to look, and H and F are different atoms. So just like when I have different atoms around the outside of my central atom, here I've just got different atoms connected, bonded together, and because they are different, they'll have different electronegativities. This will be a polar molecule. Hopefully that wasn't too bad, and you should fly through the rest of these questions on pages 5 and 6. Don't forget, I know that we didn't do the geometry words and names on 11 and 16, but we do need to look at their polarity. That's part of the reason why they are there. And C3H8 can be a little bit weird, which is why I had drawn it out for you, and I'll draw it here again. In order to get this question right with the polarity, you have to remember that carbon wants to be the central atom. And here in this C3H8, where I have 3 carbons, and they all want to be the central atom, they're kind of sharing the center of this molecule. So consider all of those carbons the central atom, and that should be able to get you your correct answer there. Even though we had a little bit of a weird structure over here on 11, it shouldn't be anything that you can't ask yourself those same 2 questions. Are there lone pairs on my central atom? Are the outer atoms different? And that should get you your same polar, non-polar answer. The only one that you're not going to be doing any polarity or IMF on is number 17. That is an ion, and ions aren't full final molecules. So this ion is ready to do an ionic compound, but that means that it's not even included in these polar, non-polar kind of set of questions. So you can scratch out the polar, non-polar space and the IMF down there. That one we're only going to do the geometry words and things on. So let me know if you have questions or issues understanding this. I'm going to stop the video here and record a separate little chunk of notes over intermolecular forces, that IMF thing that you see there, in order to be able to finish out the rest of our notes on this unit.